another topic which is an application of the things we've talked about to do with building blocks of circuit functions and asymptote constructions. Again, in the sense that this is related to a design problem or the reverse of analysis. As part of the iteration loop we talked about, eventually we make measurements and we want to compare the results with those that were predicted. And typically measurements that we make are frequency response, which would be magnitude and phase for some system. Let's suppose for the moment we don't know what the system is. So we get raw data. We get a sequence of points for magnitude and another sequence of points for phase. And the first thing we need to do is find the equivalent salient features, that is, the flat gains and the corner frequencies that these points correspond to. So we want to do a geometric construction of the asymptotes that best fit the data points. The other way around from what you do in analysis, which is given the formulas, you can draw the graphs. So the first thing to do is, in looking at the data, to take asymptotes of the proper slopes and slide them around. In this case, obviously a good starting point is the mid-band flat gain from the magnitude data points. That's the largest gain there is. This is probably the most important salient feature, so it would be good to use that gain as a reference. So you take a straight edge, a ruler, preferably a transparent ruler, and you slide it around vertically until you get the best eyeball least squares fit. That's really what you're doing by getting a straight edge. There's some experimental scatter in the points, and so you pick the straight line that's got as many points on one side of it as on the other over the straight flat region. That identifies a mid-band gain. Then you do the same thing going in one direction or the other. If we go in the low frequency direction, obviously there is a single slope in here, plus 20 dB per decade slope. So you take a straight edge with the right slope and slide it around until you get the best fit over a limited frequency range down here. Now, it's important, of course, that you use the right slope, even though you could fit the points over a wider range by taking a shallower slope. But that doesn't help. You know it's got to be a multiple of plus or minus 20 dB per decade, so you have to take the right slope. Once you've done that, of course, you've identified now a corner frequency, which is an inverted pole relative to the reference gain that we started with. All that's straightforward. If you keep on going down in frequency, then things get a little fuzzier. It looks as though the magnitude points are now beginning to flatten out again, which means you suspect that there is a zero down there, but you're not too sure, because there's only 1 or 2 points to tell you, and there's experimental error in there anyway. This means it's time to go over to the phase data and see if you can get a better idea, bearing in mind what we talked about already, that the influence of this corner, if it exists, will extend much further away from it in the phase data than it will in the magnitude data, namely a decade in phase and only an octave in magnitude. So we should use the phase data to get a better fix on the position of this zero, if there is one. Okay, the first thing to do is to check that the phase data we have is consistent with the pole that we've already identified from the first intersection. So if there's a pole there, there must be a minus 45 per decade phase asymptote to go with it. And when you draw that, you find that it fits these data points pretty well down here. But below that, obviously the phase don't fit with the same asymptote. They fall well below it. This pretty well confirms the fact that there must be a zero down here. Because if there's a zero, then it will have a plus 45 per decade slope that obviously overlaps considerably the minus 45 per decade slope that comes from the already determined pole, and in the region of overlap the phase will be flat. Well, it looks as though it is. But now you have all the information you need, because the vertical position of the flat phase asymptote is determined by the degree of overlap. And we already know where one corner is, and if we know the overlap as well, then we can pinpoint the other corner accurately by using all of the phase data in the region of overlap. So that's the procedure. I'm not going to go through the detailed solution right now, because I want to leave that for you to do as an exercise, and then I'll do the solution afterwards. But it's worthwhile, I think, for you to practice doing that and see how accurate a result you can get. So I'll leave that aside at this point. Go back to the middle now. Obviously, some other things happen towards higher frequencies, and you do the same thing. And you have to end up with a consistency between the corner frequencies obtained from both the magnitude and the phase graph. So there's a fair number of constraints. You have to have multiples of the basic slope, and you have to have the same corner frequencies from each graph. Those are the constraints that enable you to get pretty accurate results for where those corner frequencies are. However, when you do this at the high frequency end, you find a difficulty arising. It looks as though you can't fit the data points with the basic asymptotes. And I want to leave you to find out what that difficulty is. And then after you've thought about it for a bit, again, I'll go through the complete result later on. And I'll do that because the reason for that apparent discrepancy that you observe at high frequencies introduces another topic, which we're going to need to talk about in considerable detail. So I'll leave that for you to do as a sort of homework problem tonight, if you feel like it.